All right. So let's go over the homework. So the homework looked good. We're off to a good start. So I graded a number of problems from here because they're mostly fairly short problems. So a reminder, if you weren't here the first day, or if you've forgotten, make sure you look on Canvas at the section that talks about how to turn in homework. Okay, so I didn't take off points for homework style and such, but make sure you follow exactly what it's supposed to do. Clean edges, single-sided, everything from top to bottom in order, and so on and so forth. Mostly looked totally perfect. So let's just look at a few of these. So question 2, list all the elements of the following sets. And you see something like the set of 1 over n such that n is contained in the set 3, 4, 5, 6. Right? So basically you look at the conditions on n, and then for every n that satisfies those conditions, an element of the set is given by the thing to the left of the such that, so 1 over n. So the elements of the set in this case would be 1/3, 1/4, 1/5, 1/6. And if you wanted to write that as a set, you throw it in curly brackets. But technically it just said list the elements of the set, so if you just listed them side by side, that's perfectly fine. Thanks. But if it wants a set corresponding to this, then you have to put the curly brackets in. Also on the sign-in sheet, if you can please fill in the little circle next to your name. That reduces the possibility that I miss giving you credit when I fill these in. It's not too bad in this class, but in the other class it's a full page, so that helps. So that's 2A would be 1/3, 1/4, 1/5, 1/6. Part D is the set of n squared such that n equals -2, -1, 0, 1, or 2. So again, you let n be each of those possible values, and for each of those you evaluate the thing on the left of the such that. So -2 squared, -1 squared, 0 squared, 1 squared, and 2 squared. And so -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So these are the elements of the set, right? And if we were to write this as a set, we could write it like this. But we don't want to write this. That's not a valid set, right? Why? Because we're only allowed to list an element once in a set. So if you wrote that, that would technically be incorrect, even though I know what you mean. But as a set, this would be the right way to write it. All right, 1.4, B, use set builder notation to describe the following sets. So B, we have the numbers 1, 10, 100,000, and 10,000, assuming those commas are part of the numbers. That's a little confusing. So how could we write this in set builder notation? Well, they're all powers of 10, right? So that's one hint. So one way would be to say 10, the set of all 10 to the n such that n equals 0, 1, 2, 3, or 4. Or we could say the set of all 10 to the n such that n is an element of the set 0, 1, 2, 3, 4. Or you could say the set of all 10 to the n such that n is bigger than or equal to 0 and n is less than or equal to 4. And you got to be careful about the universe with this kind of thing, because what if n's 2.5? Does that count also? So I would also say something like and n is an element of the set of the integers. Or if you like natural numbers, and you could do the set of 10 to the n such that n is less than or equal to 4 and n is in the naturals. If your natural numbers include 0, but like I say, I try not to use the set of naturals in this course because there's some ambiguity in the literature. But you get the idea, right? Technically, you could do this, but I didn't give full credit for this. Could be the set of all x such that x is contained in the set 1, 10, 100, 1,000, 10,000. And yeah, that is exactly the correct set, right? And that is technically sort of a set builder notation, but it's kind of a bit of a wiggling out of the harder part of it. But we can always write S equals the set of all x such that x is contained in S. But it doesn't really capture the idea of a set builder. All right, and then I looked at, in section 2, I just looked at part B on question 4. So let the universe be the integers from 1 through 9, and give examples to illustrate the following facts. A minus B is not the same as B minus A. And you know, sometimes it is. For example, if A equals the set 1, 2, and B equals the set 3, 4, A minus B is the empty set, and so is B minus A. So sometimes A minus B and B minus A are the same thing. But that doesn't prove that they're the same. To prove that they're the same, we have to show that for any A and B that we pick, this is always true. To prove that this is not an identity, all we got to do is find one example where this fails to hold. So there's a variety of possibilities. Almost any sets you come up with, this is going to fall apart. So A minus B would be start with A, throw away everything in B. That's the set 1, 3. And that's not equal to B minus A, which is start with B, throw away everything that's A. That's just the empty set. And one example is enough to say, okay, this is not always equal. And then the other one that I graded, we actually talked about after you turn it in, which is this question: if you use universal infinite set and A and B are infinite subsets, which of these are true? Must the complement of A be finite? No, it does not have to be. Good example, U can be the set of all integers, A could be the set of even integers, which is infinite. The complement is the set of odd integers, which is also infinite. Must the union be infinite? Yes, because it contains everything in A, which is infinite, plus some other stuff maybe. Must the intersection be infinite? No. Again, evens and odds, the intersection is the empty set, which is finite. So yes, no, or no, yes, no for those. All right, so questions about homework. All right, and I posted homework already last week for this week. Any questions on that so far? We haven't gone through everything yet. Okay. So we'll take a closer look at that on Wednesday. All right, so I want to talk about a variety of things today. I want to talk about Venn diagrams, which most of us have seen at some point, but I want to run through Venn diagrams because they're useful to help visualize what's going on sometimes. And then I want to talk about membership tables. Membership tables are a way that we can rigorously prove or disprove things like A minus B equals B minus A without having to rely on coming up with lucky examples. Then I want to talk about unions of sets where you have more than two sets, and intersections and summations and products, and then we'll do some more homework questions related to those. Let's play around with Venn diagrams. So we usually have some kind of universe in mind, and we typically draw this with just a big box. And this box contains everything that we're considering. as possibly being a member of a set, right? So the universe of things. And we typically draw sets as circles. So here's a set A, here's a set B, here's a set C, and maybe here's a set D. And we imagine there's little elements scattered throughout this universal box, right? And a circle contains an element if it's, a set contains an element if its corresponding circle includes that dot. So all the things inside here are elements of A, all the things in here are elements of B. Things that are in this little funny shape where the A and B overlap, those are in both A and B, right? If there's a point right here, well, it's inside the set A, it's also inside the set B. So if we start to color code these, let's color our set A in green. And I'll color like that. And let's color our set B in the other direction. And let's do C up and down. And let's do D left and right. And we can tell some things about our sets. Again, anything inside this region right here is contained in A and also contained in B. This is the set A intersect B. Anything contained in this region or this region this is really B union C, right? Everything in this double region is either in B or in C, or it could be something that's in both. It's certainly in the union if it's in both B and C. And this little tiny piece down here, what would this little curved triangular piece be?
A intersect B intersect D.
Yeah. And we can see the associativity of this, right? We could take A intersect B, which is this tall piece right here, and find the things that are in there, and also in this pink circle, and it's just this little bent triangle on the bottom. That's A intersect B in parentheses intersected with D. We could also take A intersect D, which gives us this sort of sideways long piece, and then intersect that with B, and we get the same little piece in the middle. And visually, when we try to find where things are overlapping, it doesn't matter which ones we look at first, right? That's the associativity, and sometimes the commutativity. And if we take the set A and we throw away anything that's in B, that gives us this circle with a little bite taken out of it. That's A, take away B. And if we want just the complement of a set, well, for example, this is the set C. The complement of C in the universe, which we just call the complement, is basically all this stuff that's not in C. And that's C bar or C complement or the universal set take away C. So it's the stuff that's not shaded in C. So it's just a visual way of thinking about some of these set characteristics, these properties and operations like union and intersection and complement. And we can see from here, for example, what's the intersection of A and C? There is none, right? This circle A and this circle C do not overlap. There's nothing that's common to both of them. So their intersection is the empty set. Now it's hard to prove things with the Venn diagrams because it's just a representation. It may have nothing to do with the actual sets. We don't know, how big this overlap is. We have to do some logical mathematical work to deal with that. But visually, to get an idea what's going on, this can be a good first order way to think about the problem. And then once we understand what's going on, then we can start trying to come up with a rigorous demonstration of it. So let me give you an example of a property.
Can it ever be the case that you would consider a Venn diagram alone just the proof of something?
Yeah, I'm not going to say never. I can't think of an example where that would work, but I'm pretty sure there are cases where that would work. But in general, on a test for this course, no. But you know the four-color map theorem? So the proof for that in the 70s was a computer program, and nobody had ever seen a proof by computer program, and it was debated for a long time whether that was a valid proof or not. So there's probably something we could do here. So here's a set A, here's a set B, and I'm going to make a claim here. I'm going to claim that A union A intersect B is the same thing as A, regardless of what A and B are. If you take A and you union it with A intersect B, I claim you always get A. And we can sanity check that by looking at our diagram. So here's the set A. And here's the set A intersect B. And if we take the set A and we intersect, we add in this little piece, right? It's pretty clear we get A, right? Because this piece is actually contained in A. And in fact, I could have said something stronger. I could have said if we have A take away B and we union A intersect B, we're going to get A. Because A take away B is basically everything except that little intersection piece. And then if we add in this intersection, we get A back. So we can kind of like get some initial feeling for whether something is true or not, but we'd like to be able to prove these things rigorously. So let's try to prove this identity. And I'm not saying it explicitly, but prove for any sets A and B that this is true. Right, because certainly for some particular sets it might be true, but let's prove it for all possible sets A and B. And it's very hard to do a direct proof by just taking A and B and intersecting them and unioning it with A, because we don't know what A and B are, right? We have to show this in all possible cases. But here's what we can do. We can make something called a membership table. And here's what a membership table looks like. I'm going to imagine that we're looking at one element of the universe. And I don't know which element it is, but we're picking one element of the universe. And I'm going to ask the following question. Is that element a member of set A? And the answer is either yes or no, right? And then I'm going to ask, is that element a member of set B? And the answer is either yes or no. So for any element I pick, there's exactly 4 possibilities. It may be that that element does not belong to A and it does not belong to B. Or it does not belong to A, but it does belong to B. Or it belongs to A and not B. Or it belongs to both A and B. Are there any other possibilities? Right, there's only 4 possible combined situations. Because for A it's either a member or not, for B it's either a member or not. So any element you pick, one of these 4 conditions will be true, exactly one of them. So if I can prove that in each of these 4 possibilities this identity holds, then I've proven that this is always true. So let's think about A intersect B. Suppose we pick this one element, and it's not a member of A and it's not a member of B. Is it a member of A intersect B? Right? Absolutely not. Because to be a member of A intersect B, it means it has to belong to A and it has to belong to B. So if it's not in A, we know it's not in the intersection. And if it's not in B, it can't be in both A and B. But in this 4th case, if it belongs to A and it belongs to B, does it belong to the intersection? Yep. That's exactly what it means to say it's in the intersection. So here's a membership table for an intersection. Okay, now pick some element. It's not a member of A, it's not a member of the intersection. Is it a member of A union that intersection? It's not in this thing and it's not in that thing. Can it be in the union? No. It's in A, but it's not in the intersection. But it's in A. Is it going to be in the union of those? Yes. And if it's in A and it's in the intersection, it's definitely in the union of those. So for any element we pick, that element will belong to A union A intersect B exactly when that element belongs to A. Right? Because these and these are exactly the same values for all elements in the universe. So any element X is contained in A. Remember what IFF means? If and only if X is contained in A, if and only if X is contained in A union A intersect B. And this was our definition of equality. So we can say therefore, and we abbreviate therefore with 3 dots in a triangle, therefore A is equal to A union A intersect B. And so that's enough to say we formally proved that this identity is true. And just for completeness, let's fill in a column for A union B for all possible cases. If an element's not in A or B, we know it's not in their union. If it's not in A but it's in B, is it in the union of A and B? And if it's in A but not B, is it in the union? And if it's in both, it's certainly in the union. So here's the membership table for a union operation. And what does this look like from Engineering 250? Looks like an and what does this look like? Looks like an or. And in fact, this looks an awful lot like that, and this looks an awful lot like that. That's deliberate. So unions are really just ors, and intersections are really just ands. And that's kind of cool. What about A take away B? If something's not in A to begin with, it's not in A take away B, right? So if something's not in A, these are zeros. If something is in A and not in B, it's still going to be in A take away B. But if it's in A and it's also in B, then it's not going to be in this subtraction. So that doesn't really map nicely to something in 250. Well, it does. But so these are just truth tables, right? And everything you've done with truth tables in 250 basically works for membership tables in here. So you can prove De Morgan's theorem and adjacency and absorption and all these other things. And they just look like you're doing truth table proofs from the beginning of Engineering 250. All right, questions on this?
So Venn diagram proofs with air quotes on it are not accepted.
Correct.
Are membership table proofs
Yes.
acceptable?
Unless I say don't use a membership table to prove this. Right, which I could do, but probably won't. So the other way, so digital logic, right? Mostly if you want to prove something's true, we jump to a truth table. If the instructions say don't use a truth table, what do? You have to use identities, right? So you use the fact that you've got distribution and De Morgan's theorem, absorption, and things like that, and you put those together. And we don't usually do that a lot in 250, but we won't do it a lot in here. There's other things we'll spend our time proving. Usually membership tables are a good way to go. All right, so let's talk about unions and intersections. We've already discussed these, but let me show you some notation. Sometimes we might have a collection of sets. For example, I might have set A1 equals ABC, and A2 equals ACE, and A3 equals BCDEF. And I might ask the question, what is A1 intersect A2 intersect A3? I'm not going to ask it, but I might, right? And if we had a lot of sets, we could do, the intersection of 15 things. There's a shorthand you'll see sometimes. We could take this, and we could write it more succinctly as the intersection from I equals 1 to 3 of A subscript I. And it's just a notational shorthand. A1 intersect A2 intersect A3. And it's kind of like a summation symbol, which we're going to review too. This is kind of like a for loop in programming. Saying for I equals 1 to 3, let's take the intersection of A subscript I with whatever else we're intersecting. And you'll see a union from K equals 1 to 5 of, S sub K or whatever. And one thing to keep in mind, this expression right here, if I had said the intersection from j equals 1 to 3 of a subscript j, is that any different from this? It's exactly the same thing. Just like when you write a for loop, it doesn't matter if you say for I equals 1 to 10 or for j equals 1 to 10, as long as you use I or j in the appropriate spot inside the loop. Right, so it's really kind of a arbitrary, temporary variable. Although I know somebody who was at a university and they got their programming assignment back and they lost points because they said for j equals 1 to 10, and the teacher said I is the traditional variable for loops. He took off points because he used j. I won't do that to you, but all right, so we can change variables, and sometimes it's useful to change variables. Let me show you another expression that would be equivalent. Same thing. Intersection from 0 to 2 of a sub I plus 1. I equals 0, this is a1. I equals 1, this is a2. I equals 2, this is a3. And we do this in programming too. We go from 0 to 9, we go from 1 to 10, we go from 100 to 109, as long as you do the right thing inside the loop. All right, and then last thing I want to go over in this is summations and products. So you've probably seen this notation. Right, the sigma I equals 1 to n of something up here. Let me just call it some function of I. And this is another shorthand. This means f of 1 plus f of 2 plus f of 3 all the way up to f of n. So it's another loop basically. It's a running sum. And we'll also be able to say the product from I equals a to b of some function of I. That would be f of a times f of a plus 1 times f of a plus 2 times all the way up to f of b. Is there any worries on any of this? The other thing is these things can nest. So we could say the sum from I equals 1 to 3 of the sum from j equals 2 to 4 of I times j. And ask what that is. And if you see something like this, an easy way to deal with this is break things into groups. First, just look at this innermost loop and write out what this is. This says set j equal to 2 and evaluate the expression I times j. Well, that's I times 2. And then set j equal to 3 and evaluate I times j. That's I times 3. And then set j equal to 4 and evaluate I times j. That's I times 4. And add these together. And if you do that, this turns out to be 9 times I. So we can rewrite this as the sum from I equals 1 to 3 of 9 times I. And what's that? Set I equal to 1. 9 times 1, set I equal to 2. 9 times 2, set I equal to 3. 9 times 3. And that looks just like a nested for loop, right? This inner thing happens from 2 to 4, and each time that I changes, we redo that inner loop. All right, so just break things into pieces if it helps. So your homework comes from 1.5, 3.1, 3.2, and 3.3. So we're going to start chapter 3 tomorrow. So 1.5, questions 2, 4, and 10. So question 2, you're just calculating some series expressions. So again, just plug in the values for J and calculate these. Question 4, verify the following properties. So this is another one that I want you to think about and ask questions on. It's pretty obvious what 4a is saying, right? We can take that summation and we can break it into two summations. We know that, right? We've learned that when we first learned about summations. Or if each term is multiplied by c, we can just pull that c outside the summation. But think about how you would actually prove that, right? And then show for n equals 3 that these things are true. And this is subtle. It's one of these things that's so clear to us that it's really hard to prove, right? It's like proving that we exist. That was a huge problem for philosophy for a long time. Descartes cracked this nut. But how do you prove that you exist? I mean, it's so obvious that it's almost impossible to dream up a proof. So pick n equals 3 and see what you can do to actually show that these things are true. And then question 10 is, did I really give you question 10? Interesting. Yeah, I did. Oh yeah, I remember that. Okay. Yeah, so part A is straightforward. Part B, don't multiply 100 things together on your calculator. Okay, that's too much work. Be lazy. Think about how you can do this with less work. Okay, so product from k equals 1 to 100 of k over k plus 1. And then we'll be working on chapter 3, possibly later today and then definitely on Wednesday. So we'll talk about those later. All right, good. So let's take a few minutes break. Let's come back at like 17 after, and we'll start working on some more set problems on the boards.